Welcome to this walkthrough of LeetCode problem number 2191, Sort the Jumbled Numbers. In this session, we'll explore how to solve this interesting problem, which involves sorting an array based on transformed values of its elements. Let's dive in and uncover the approach step by step. In this problem, we are given two key inputs. First, there's a mapping array called mapping. This array has 10 elements, where each element corresponds to the transformation of a digit from 0 to 9. For example, if mapping 2 is 4, it means the digit 2 will be transformed into 4. Alongside this, we are given another array called nums, which contains a list of non-negative integers. Each number in nums will be transformed digit by digit using the mapping array. The transformation process involves converting each number into its string form, replacing each digit in the string with its corresponding transformed value from mapping, and then converting the result back into an integer. Once all the numbers are transformed, we sort the nums array based on these transformed values. Importantly, if two numbers result in the same transformed value, their original order in the nums array is preserved. Our task is to return the sorted version of nums after this transformation and sorting process. To clarify the input and output formats, the mapping array has exactly 10 integers, where each integer represents the new digit for 0 through 9. The second input, nums, is a list of non-negative integers. The output is the nums array, but sorted according to their transformed values. Let's look at an example to make this clear. Suppose mapping equals 2, 1, 4, 8, 6, 3, 0, 9, 7, 5, and nums equals 990, 332, 981. After applying the transformation, the number 990 becomes 554, 332 becomes 888, and 981 becomes 576. When we sort these transformed values, we get 554, 576, and 888, which corresponds to the original numbers 981, 990, and 332. Therefore, the output of this example is 981, 990, 332. Let's break down the reasoning for example 1. Starting with the given inputs, mapping equals 2, 1, 4, 8, 6, 3, 0, 9, 7, 5, and nums equals 990, 332, 981, we transform each number using the mapping. The number 990 transforms into 554, because the digit 9 maps to 5 and the digit 0 maps to 4. Similarly, the number 332 transforms into 888, as the digit 3 maps to 8 and the digit 2 maps to 8. Lastly, 981 becomes 576, since 9 maps to 5, 8 maps to 7, and 1 maps to 6. After transformation, the resulting values are 554, 888, and 576. Sorting these values gives 554, 576, and 888. Finally, we map these sorted values back to their corresponding original numbers in nums, which produces the result, 981, 990, 332. Now let's consider example 2, where the input mapping is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and nums is 789, 456, 123. Here, the mapping is an identity mapping, meaning each digit maps to itself. This means the transformation doesn't change the numbers. 789 remains 789, 456 remains 456, and 123 remains 123. Since the transformed values are identical to the original values, the sorting is based directly on the original numbers. Sorting 123, 456, and 789 in ascending order gives 123, 456, 789, which is the final output. In example 3, the input mapping is 1, 0, 3, 5, 9, 8, 6, 4, 2, 7, and nums is 0, 1, 2, 3, 4. Let's transform each number. The digit 0 maps to 1, so 0 becomes 1. The digit 1 maps to 0, so 1 becomes 0. Similarly, 2 becomes 3, 3 becomes 5, and 4 becomes 9. Thus, the transformed values are 1, 0, 3, 5, 9. Sorting these transformed values gives 0, 1, 3, 5, 9. Finally, we match these sorted transformed values back to their original numbers, resulting in 1, 0, 2, 3, 4. This is the output for this example. Now let's discuss some edge cases and the constraints. If nums contains only one number, the output is simply the input, since sorting is unnecessary. For instance, with mapping equals 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and nums equals 0, the output is 0. Another case to consider is when the mapping is an identity mapping. In such cases, the transformed values are the same as the original values, so the output is simply the sorted version of nums. For example, if nums equals 5, 3, 8, the output is 3, 5, 8. Finally, if two numbers transform into the same value, the original order is preserved. For instance, with nums equals 12, 21, and the identity mapping, both numbers transform to 12, so the output is 12, 21. The time complexity of this solution involves processing all digits in nums, which is proportional to the total number of digits. With n numbers and an average of d digits per number, the complexity is O, d asterisk n plus n asterisk log n. The space complexity is O, n, for storing the transformed values. To solve LeetCode problem number 2191, the task is to sort an array of numbers, nums, based on a transformed version of their digits. This transformation is defined by a mapping array, where each digit in a number gets replaced by its corresponding value in the mapping. One straightforward approach we can consider is the brute force method. In this approach, we first define a helper function to transform each number by replacing its digits according to the mapping. Then, we compute the transformed value for each number, pair it with the original number as original, transformed, and sort these pairs based on the transformed values. When there are ties, the original numbers act as tiebreakers. Finally, we extract the original numbers in their new sorted order. This method involves transforming every number digit by digit, sorting the pairs, and then reconstructing the result. While the overall complexity of this method is acceptable for smaller inputs, it becomes less efficient for larger datasets due to the redundant calculations involved during sorting. The brute force approach, while straightforward, has some notable drawbacks. The main inefficiency lies in the fact that the transformation is computed repeatedly during the sorting process. This can lead to significant overhead, especially when the input size grows. To address this inefficiency, we can adopt an optimized approach by pre-computing the transformed values beforehand. In this method, we iterate through each number in nums, transform its digits using the mapping array, and store the transformed value alongside the original number as a transformed original pair. Once this pre-processing step is complete, we can sort the array of pairs using the transformed values as the primary sorting key and the original numbers to break any ties. After sorting, we extract and return the original numbers in their new order. By pre-computing the transformations, we avoid recalculating them during sorting, which significantly reduces redundant operations and leads to a more efficient solution. The optimized approach offers several benefits. First, it eliminates redundant calculations by encapsulating the transformation in a pre-processing step, which simplifies the sorting logic. This separation of concerns allows us to focus solely on efficiently sorting the pre-computed pairs, making the method cleaner and faster. Additionally, this approach is well suited for inputs with larger sizes, as the transformation step is performed only once for each number. However, there is a trade-off: we need additional memory to store the transformed values temporarily. Despite this, the optimized approach is the preferred strategy because it strikes a good balance between simplicity, efficiency, and clarity. The key insight here is that the transformation is digit-wise, meaning it does not depend on the positions of the digits. This allows us to transform the digits of a number independently. Furthermore, using both the transformed values and the original numbers for tiebreaking ensures that the sorting process is accurate and preserves the required order. When comparing the brute force and optimized approaches, the differences become clear. The brute force method involves recomputing the transformation for each number during sorting, which introduces unnecessary overhead. In contrast, the optimized approach pre-computes these transformations, resulting in cleaner and more efficient sorting logic. However, this optimization comes with a trade-off in memory usage, as we need to store the transformed values temporarily. Despite this, the optimized method is better suited for larger inputs due to its scalability and reduced computational redundancy. Overall, the optimized approach is preferred because it provides a clear balance between performance and resource usage, making it the ideal solution for this problem. To tackle the problem of sorting the numbers in nums based on their transformed values, the first step is to understand how the transformation works. Each digit within a number is replaced by its corresponding value in the mapping array. For instance, if the mapping array is given as 2, 1, 4, 8, 6, 3, 0, 9, 7, 5, the digits of the number 990 are transformed as 9 becomes 5 and 0 becomes 2, resulting in the transformed number 552. Once we understand this process, the next step involves creating pairs of the original number and its transformed counterpart. This can be represented as a list of tuples, such as original_number, transformed_number. For example, with nums equals 990, 332, 981, the transformed list would be 990, 552, 332, 844, 981, 513. Lastly, the sorting criteria are defined. The transformed number is the primary criterion for sorting, while the original number is used to break ties, ensuring the relative order of numbers with the same transformed value is maintained. This stability in sorting is an important aspect of the solution. Now, let's see how to implement the solution efficiently. For each number in nums, we need to transform it by replacing its digits using the mapping array. This involves iterating through each digit, applying the mapping, and reconstructing the transformed number by concatenating the mapped digits. Once the transformation is complete, the next step is to sort the list of pairs. Using Python's built-in sorted, or sort, functions with a custom key allows us to sort the pairs by their transformed values while ensuring stability. After sorting, the final step is to extract the original numbers from the sorted list of tuples. The result is the sorted version of nums based on the transformed values. Some key insights here include the efficiency of the digit mapping process, which works in O(k) time for a number with k digits, and the convenience of pairing the original and transformed values, which allows easy retrieval of the original numbers after sorting. Python's sorting functions are stable, which means if two keys are equal, the relative order from the input is preserved in the output. This property is crucial for handling ties, as the original numbers act as tiebreakers during sorting. In terms of efficiency, the algorithm processes each number individually to perform the transformation, which takes (k) time for n numbers with an average of k digits each. Sorting the resulting list of tuples takes (n log n), making the overall algorithm efficient even for larger inputs. To implement this, we use simple data structures. The mapping array, which stores the digit mapping, allows O(1) access per digit. A list of tuples is used to store pairs of original and transformed numbers, which simplifies sorting. The algorithm is then implemented step by step in code. First, we iterate over the numbers in nums, map their digits one by one using the mapping array, and reconstruct the transformed numbers. These are paired with their original counterparts and stored in a list for sorting. After the transformation, sorting the list of tuples is the next critical step. Using Python's built-in sorted, or sorted function, we specify a custom key that sorts the tuples first by the transformed value and then by the original number. This ensures the correct order based on the transformation while maintaining stability. Once the list is sorted, the final step is to extract the original numbers from the sorted tuples. This is easily achieved using a list comprehension that picks the first element of each tuple. The output is the sorted version of the original array nums. To summarize the key operations, the algorithm first performs digit replacement by extracting and mapping each digit, reconstructs the transformed number, sorts the pairs based on the custom criteria, and finally extracts the sorted original numbers. Each of these operations is efficient and leverages Python's robust built-in features. The final complexity analysis helps confirm the algorithm's scalability. The time complexity of the algorithm can be broken down into two main components. Transforming all numbers takes (n*k), where n is the number of elements in nums and k is the average number of digits per number. Sorting the list of tuples takes (n log n), leading to an overall complexity of (n*k plus n log n). The space complexity is (n), due to the list of tuples used to pair the original and transformed numbers. Additionally, the algorithm handles a variety of edge cases gracefully. For example, when all numbers are single digits, the transformation is straightforward since each number is directly mapped using the mapping array. Duplicate numbers are handled seamlessly due to the stability of Python sort. The algorithm also efficiently processes large numbers, as Python supports arbitrary precision integers. Finally, for an empty input, the algorithm simply returns an empty list without errors. This robustness ensures the solution is versatile across different scenarios. This solution efficiently sorts the array nums based on a transformed version of each number using the provided mapping. Here's a line-by-line breakdown of the code. 1. Defining the class and method. The sort jumbled method is implemented inside the solution class, which is standard for LeetCode problems. 2. Transform function. The transform function takes a number and transforms it into a new number by replacing each digit using the mapping array. This is done by iterating through the digits of the number in reverse order, least significant digit first, replacing each digit with its mapped value, and reconstructing the transformed number. 3. Creating transformed pairs. For each number in nums, we create a tuple, transformed_value, index, original_number. The index is added to ensure stable sorting in case of ties. For sorting the pairs, the transformed_pairs list is sorted using a lambda key function. The key sorts primarily by the transformed value and secondarily by the original index to maintain stability. 5. Extracting the sorted numbers. After sorting, the original numbers are extracted from the sorted list of tuples, resulting in the final sorted array. This approach ensures that the transformation and sorting processes are efficient. The complexity of the solution is determined by the transformation of each number, O, D, where D is the number of digits, and the sorting step, O, n log n, for n numbers, resulting in an overall time complexity of approximately O, n log n. The solution handles all edge cases, including empty input, single-element arrays, and cases where all numbers map to the same transformed value. Here, we start by importing the necessary libraries and defining the solution class with the sort jumbled method. The method takes two parameters, an array called mapping, which defines how each digit from 0 to 9 is transformed, and an array nums, which contains the numbers we need to sort. To facilitate this process, we define a helper method named transform to convert a given number based on the mapping. If the number is 0, we explicitly return the mapped value of 0. For non-zero numbers, we iterate through each digit, apply the mapping to it, and construct the transformed number digit by digit. This is done using a while loop where we repeatedly extract the last digit using modulus, apply the mapping, and build the transformed number. Once we have the helper method, we create a list called transformed pairs to store three pieces of information for each number: the transformed value, the original index, and the original number itself. This is important because we will later use this list for sorting while preserving the original indices to break ties when necessary. Now that we have the transformed pairs list, the next step is to sort it. To do this, we use the sort method with a custom comparator. If the transformed values of two pairs are different, we sort them based on the transformed values in ascending order. However, if the transformed values are the same, we break the tie by comparing their original indices, ensuring that the relative order of numbers with the same transformed value remains consistent with their initial positions. After sorting, we extract the original numbers from the sorted transformed pairs list and store them in an array called result. Finally, we return the result array, which contains the numbers from nums sorted according to the transformation rules defined by the mapping. This implementation is efficient and ensures that all edge cases, such as zero handling and tie breaking, are properly addressed. In this problem, we are tasked with sorting an array of integers based on a digit mapping provided in the form of another array. The key challenge lies in transforming each number using this mapping and then sorting them based on their transformed values. Importantly, if two numbers share the same transformed value, we must maintain their original order from the input array. To better understand this, let's look at an example. Consider the mapping array 2, 1, 4, 8, 6, 3, 0, 9, 7, 5, and the input array of numbers 990, 332, 981. The first step involves transforming each number by substituting its digits using the mapping. For 990, the digits are 9, 9, and 0. Using the mapping, these digits transform to 5, 5, and 2, resulting in the transformed value 552. Similarly, for 332, the digits transform to 884 by mapping 3 to 8 and 2 to 4. For the number 981, we transform the digits 9, 8, and 1 using the mapping. 9 becomes 5, 8 becomes 7, and 1 becomes 1, giving us a transformed value of 571. Now that we have the transformed values for all numbers, we pair each original number with its transformed value and its original index. This results in the list 552, 0, 990, 884, 1, 332, 571, 2, 981. Next, we sort these pairs based on the transformed values, breaking any ties by using the original indices. After sorting, the list becomes 552, 0, 990, 571, 2, 981, 884, 1, 332. Finally, we extract the original numbers from these sorted pairs to get the result, 990, 981, 332. This is the output of the example. Now let's explore a case where all transformed values turn out to be equal. Consider the mapping array 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, and the input numbers 12, 34, 56, 78. Since every digit maps to 1, each number transforms into the same value. For example, 12 transforms to 11, 34 also transforms to 11, and so on for 56 and 78. This gives us the transformed values 11, 11, 11, 11. We then pair these transformed values with their respective indices and original numbers, resulting in 11, 0, 12, 11, 1, 34, 11, 2, 56, 11, 3, 78. Because all transformed values are identical, the sorting step preserves the original order based on the indices. Extracting the original numbers gives us the final sorted output, 12, 34, 56, 78. To further illustrate, let's examine a case with mixed transformed values. Suppose the mapping array is 9, 8, 7, 6, 5, 4, 3, 2, 1, 0, and the input numbers are 123, 456, 789, 101. For 123, the digits 1, 2, and 3 transform into 8, 7, and 6, giving a transformed value of 876. Similarly, for 456, the digits 4, 5, and 6 transform into 5, 4, and 3, resulting in 543. For 789, the digits 7, 8, and 9 transform to 2, 1, and 0, yielding 210. Finally, for 101, the digits 1, 0, and 1 transform into 8, 9, and 8, producing the value 898. Now that we have all the transformed values, we pair each number with its transformed value and index, resulting in 876, 0, 123, 543, 1, 456, 210, 2, 789, 898, 3, 101. Next, we sort these pairs based on the transformed values, resolving any ties using the original indices. After sorting, the list becomes 210, 2, 789, 543, 1, 456, 876, 0, 123, 898, 3, 101. Extracting the original numbers from this sorted list gives us the final output, 789, 456, 123, 101. This demonstrates how the algorithm handles cases with varying transformed values while preserving stability in the sorting process. Let's break down the time complexity of the solution step by step. First, we have the transformation process. The transform function processes each number digit by digit. For a single number with d digits, this operation takes O(d) in time. Now, if there are n numbers in the input list nums and the maximum number of digits in any number is d, the transformation step will take O(n*d) time in the worst case. Next, we move to sorting. After transforming the numbers, we create a list of tuples called transformed_pairs. Each tuple contains the transformed number, its original index, and the original number. Sorting this list of n tuples is an O(n*log n) operation. Finally, there's the step of extracting results. This involves iterating through the sorted list of tuples to gather the sorted numbers, which is an O(n) operation. By analyzing these steps, we can see that transformation and sorting are the dominant contributors to the total time complexity. When we combine the complexities of transformation and sorting, the overall time complexity of the solution becomes O(n*d plus n*log n). Now let's consider space complexity. For the transformation step, the transform function processes one number at a time, requiring only O1 auxiliary space. Since transformations are performed sequentially, this step has constant space usage. However, storing the transformed pairs requires additional space. These pairs include the transformed number, the original index, and the original number for each of the n elements, resulting in O(n) space. Sorting also adds to the space complexity. Python's timsort algorithm, which is used for sorting, has a worst-case auxiliary space complexity of O(n). When we combine these, the overall space complexity of the solution can be determined. The space complexity of the solution is O(n), as the storage for transformed pairs and timsort's auxiliary space both scale linearly with the size of the input. Now let's analyze the algorithm in different scenarios. In the best case, where all the numbers are already sorted after transformation, the sorting step still takes log n time, as the sorting algorithm needs to verify the order. For both the average and worst cases, the time complexity remains the same because the algorithm does not exploit specific input patterns to optimize performance. Comparing this solution to a naive approach highlights its efficiency. A naive method, which would compare transformed values for every pair of numbers, would result in O(n²d) time complexity due to the pairwise comparisons. This is far less efficient than the proposed solution, which uses sorting to reduce the complexity to O(n*d plus n*log n. Finally, let's solidify the reasoning behind these big O complexities. The transformation step processes each number in proportion to its digits, leading to O(n*d). Sorting, which is typically the dominant operation for large n, has a time complexity of O(n*log n. However, d, representing the maximum number of digits, can grow in extreme cases, such as when dealing with very large integers. This is why both terms, O(n*d) and O(n*log n, are included in the total time complexity. For space complexity, the transformed pairs and the auxiliary storage used during sorting both grow linearly with the input size, resulting in an overall space complexity of O(n). This balance between time and space usage makes the algorithm efficient for solving the problem within the given constraints. In this section, we'll look at some common mistakes that programmers make when solving the sort the jumbled numbers problem and how to avoid them. First, not handling leading zeros in transformed numbers can lead to incorrect results. For example, when mapping digits using the mapping array, numbers like 0, 0, 1 and 1 might seem equivalent if leading zeros are ignored, but their transformed values could be entirely different. To fix this, you can explicitly handle leading zeros by working with string representations of numbers or ensuring that the transformation logic accounts for them correctly. Another common issue is implementing the mapping incorrectly. For instance, some mistakenly treat mapping I as an index instead of the value to replace the digit I. This leads to transformed numbers that don't align with the problem's requirements, and consequently, the sorting will be incorrect. To address this, it's crucial to carefully verify the mapping logic and test your solution with a variety of edge cases to ensure correctness. Now, let's discuss additional pitfalls. Inefficient sorting approaches can significantly slow down your solution. A common mistake is reconstructing the transformed numbers repeatedly inside the sorting function, which increases the time complexity unnecessarily, especially for large input arrays. To optimize this, pre-compute the transformed values and pair them with the original numbers in a list of tuples, so you can sort efficiently without redundant computations. Another issue is ignoring the stability of the sorting algorithm. The problem explicitly requires you to maintain the relative order of numbers with identical transformed values, but using an unstable sorting algorithm like quicksort can violate this requirement. Instead, opt for stable sorting methods such as Python sorted or C++ SSTD stable_sort. Lastly, it's easy to overlook edge cases such as empty input arrays, single element arrays, or mappings where all digits map to the same value. If these cases aren't handled properly, your solution might fail or produce incorrect results. Testing with diverse edge cases is essential to ensure the robustness of your implementation. This problem also has important interview insights to consider. It primarily tests your ability to transform data, implement custom sorting logic, and maintain sorting stability. Attention to detail is critical, as you need to follow constraints like preserving the relative order of numbers with identical transformed values. One key pattern here is the pre-computation of transformed values. By pairing each transformed number with its original counterpart, you can sort efficiently and avoid unnecessary recalculations. Optimizing for time complexity is another important focus. Redundant computations, like recalculating transformed numbers during sorting, can be avoided with pre-computation. During an interview, it's also valuable to discuss trade-offs. For example, pre-computing transformed numbers may increase space usage, but it significantly reduces the runtime of the sorting step. Lastly, always demonstrate your ability to handle tricky inputs, such as duplicate numbers or transformed values that are identical. These details can make or break your solution during an interview. It's also helpful to explore related problems that share similar concepts. For instance, LeetCode 937, Reorder Data in Log Files, focuses on sorting based on custom criteria while maintaining relative order, which aligns closely with this problem. Another example is LeetCode 791, Custom Sort String, where you define a custom sorting priority, much like the mapping logic here. LeetCode 75, Sort Colors, involves sorting under constraints, though it emphasizes in-place operations rather than transformation-based sorting. Finally, there's LeetCode 1122, Relative Sort Array, which involves sorting based on a specific order defined externally. These problems are great practice for strengthening your understanding of custom sorting logic and handling constraints effectively. Finally, let's look at alternative approaches and their trade-offs. One option is to perform inline transformation during the sorting process. This approach saves memory by avoiding pre-computations but increases the time complexity due to redundant transformations of numbers while sorting. It's best suited for small input sizes where performance isn't a concern. Another approach involves using a hash map to pre-compute and store transformed values. This method improves lookup efficiency during sorting, especially when the input contains many duplicate numbers, as the hash map prevents redundant transformations. However, it increases space complexity. Lastly, you could use a custom comparator with a stable sorting algorithm. This allows you to define the sorting order based on transformed values explicitly. The effectiveness of this approach depends on the stability of the underlying sorting algorithm. In languages like Java or C++, custom comparators integrate seamlessly with built-in sorting functions, making this a powerful alternative in those environments. Great job! To recap, we solved the problem by applying a mapping transformation, sorting based on the transformed values, and ensuring stability. This approach highlights the importance of combining sorting techniques with problem-specific logic. Keep practicing to sharpen your skills. Thanks for watching, and see you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!